Hi all, today in 7.3 we're going to be exploring the log and the exponential functions with other bases. So what I'd first like to do is look at the limit of, and this first graph here is actually the graph of natural log of x. And here that not having arrows is going to totally irritate me. So let's go ahead and review some limits. If you look at this graph and you want to evaluate the limit as x goes to infinity of natural log of x, well, as x goes to infinity, the y values are also going to go to infinity. And then if we look at the limit as x goes to 0, and here we're going to approach 0 from the right, of the natural log of x, the graph goes down to negative infinity. So on this second graph, the function that goes high to low would be y equal to e to the negative x, or 1 over e to the x. And then this function that goes low to high is y equal to e to the x. So if we look at the limit as x goes to infinity of e to the x, so as x goes to infinity, our function e to the x goes to positive infinity. And the limit as x goes to negative infinity of e to the x is 0. So the limit as x goes to infinity of e to the negative x is the opposite. That would be the 0. And then the limit as x goes to negative x of e to the negative x, that's actually going to be positive infinity. Okay. So let's explore these properties of limits. So in example 1a, we want to find the limit as x goes to infinity of e to the 5 minus x. Okay. So note that we just plug in infinity and we get e to the 5 minus infinity. And then 5 minus infinity is just e to the negative infinity. So when you think about that, e to the negative infinity is actually 0 because it's 1 over e to the infinity. So recall, if your numerator is constant, but the denominator is getting larger and larger and larger, closer to infinity, the whole fraction is actually approaching 0. Okay, so let's look at example B. When we take the limit as we approach 4 from the left, that's going to be equal to let's see, that's equal to e to the 1 over 0. So I really don't know what that means. So what I'm going to do is, since our exponential function is continuous, what I'm allowed to do is take my limit into the argument. So this is actually equal to e. I can bring the limit up here. And just look at the limit, 1 over x minus 4. So that's going to be e to the 1 over 0. But think about this. My x's are approaching 4 from the left, so they're smaller than 4. So this denominator is going to be negative, right? Which means this is e to the negative infinity. And that is 0. All right, let's do another example with limits. Okay, so if I evaluate this limit, it looks like natural log of e is 1, so it looks like it's going to be 0 over 0. So just remember that that's an indeterminate case. It doesn't mean 0, it doesn't mean the limit does not exist. It means you have to do something more. So I'm not sure if you recall L'Hopital's rule, and we'll go over L'Hopital's rule again in a later section. That says that if you get the indeterminate form 0 over 0, we're allowed to reevaluate the limit by taking the derivative of the top and the bottom separately. So the derivative of natural log of x minus 1 is just 1 over x. And the derivative of the denominator, x minus e, is 1. Okay? So when we reevaluate this limit, we just get 1 over e. Okay, so let's move on to the next page. We're going to look at the log function of any base b, not just the natural log function. So first of all, this is just to recall that y equal log base b of x is actually x is equal to b to the y. And then if we look at some of the relationships for the log function says that if you take your base and you raise it to log base b, these cancel. Okay, and all you have left is the x. And if the base and the argument match, they cancel, and you just have x. So we're going to look at the derivative of any base b to the x, and we're going to compute the derivative. Okay, so we want to prove this derivative, and we haven't done many proofs in this class, but this is a really nice proof. And so first of all, what I'd like you to note is that b to the x by one of our properties is actually equal to, we could rewrite it as e to the natural log of b to the x. And what that will allow me to do is to bring the x out from the exponent. So we have e to the x times the natural log of b. So when I take the derivative with respect to x on both sides of this equation, I don't really know what this left-hand side is. That's actually what I'm trying to prove, okay? But I do know what the right-hand side is, because I know how to compute the derivative, right? The derivative of the exponential function says it stays the same. So e to the x natural log of b times the derivative with respect to x of x times natural log of b, okay, by the chain rule. But the natural log of b is just a constant, right, like 2. So when I take the derivative of x times natural log of b, it's just natural log of b. Okay? So this right-hand side is going to be e to the x times the natural log of b times the natural log of b. Okay, but recall what this was equal to. That's b to the x from the beginning. Okay? So therefore, the derivative with respect to x of b to the x is equal to b to the x times the natural log of b. So all that says is it stays the same times natural log of the base. So let's go ahead and compute some derivatives. This is super nice. if I wanted to find the derivative of y equal to a to the x, the derivative stays the same times the natural log of the base 8. And that's it. So let's try something a little more challenging. So this is going to involve the chain rule. When we look at example B, I have the derivative is equal to, stays the same, times the base. Okay, and then it's going to be times the derivative with respect to x of 3x squared. So again, we had to use the chain rule here. And that's just going to be 6x. So putting this all together, we have the derivative is equal to 8 3x squared times the natural log of 8 times 6x. And typically I like to put the 6x in the front, so there's no confusion on whether it belongs to the natural log or not, which it doesn't. And I'm done. Okay, so let's go on to the next page. And this is a really nice example, example number 3, because notice that y is sine of x to the x power. So it actually doesn't fit the criteria of what we did before. The reason why is because the base is a function of x. It's sine of x. It's not some number to the power of x. So we have to be careful. One thing we could do is we could do logarithmic differentiation. But I think I'm going to try something a little different. What I'm going to do is I'm going to rewrite sine of x to the power of x as e to the natural log of sine of x to the power of x. What that will allow me to do, and notice I haven't even taken the derivative yet, it allows me to take the x from the exponent and bring it out in front of our natural log. So now I've rewritten my function y as the exponential function. And remember, that's really easy when you take the derivative of the exponential function. It stays the same times the derivative of the exponent, which is x times the natural log of sine of x. And this is the product rule, because I'm taking the derivative of a function of x times a function of x. So the product rule says derivative of x is 1, natural log of sine x stays the same, plus x stays the same. The derivative of the natural log of sine x is 1 over sine of x times the derivative of sine of x, which is cosine of x. So you have to use the chain rule there. Okay, so I'm going to put all this together as, but I'm going to rewrite this piece here, because remember, originally that was just sine of x to the power of x times, and then it's multiplied by all of this. This is all one piece, natural log sine of x, so don't forget your parentheses or brackets, plus x times cosine over sine. I could write that as cotangent and it will look a lot nicer. Okay, so there's no need to distribute the sine of x to the power of x. You can stop here. All right, so let's look at integrals. So if we're looking at integrals for any base, okay, it's going to stay the same but then we're going to multiply by 1 over natural log of b. So kind of opposite of what the derivative is. So in example 4, I'm going to evaluate the integral of 5 to the 6x. Now remember, this is not just x, it's 6x. So I need to do a substitution. I need to let u equal 6x. So my du over dx is 6, or in other words, du over 6 is x, dx. Erase that. Okay, so my integral is going to be the integral of 5u times du over 6. Or in other words, 1/6 integral of 5u du. So now it looks like the theorem 7.8. It's going to stay the same times 1 over natural log of the base, plus a constant c, because this is an indefinite integral, but then we have to substitute back for our u, which is 6x. So again, let me clean all of this up. It becomes 5 to the 6x over 6 times the natural log of 5 plus our constant c. All right, so let's look at the second example. The integral of 1 over the natural log of pi to the x power. This is a little bit weird. I don't even know what this means. But notice that because of my log properties, I can take the x in the exponent and bring it out in front to say x times natural log of pi. And then 1 over the natural log of pi is a constant, right? I can bring that out. And this is actually the integral of 1 over x dx. So recall what that is. That's just the natural log of x. We just have to remember that it's going to be times the natural log of the absolute value of x. An indefinite integral, it would be plus the constant c. And I'm okay if you just leave it like this, or if you wish, you could write it as the natural log absolute value of x over natural log of pi plus c. All right, let's go on to the next page. I really wanted to look at these next two examples because sometimes it's confusing about what property we're supposed to be using. So if you look at example A, it's a function of x raised to the power of pi. Pi is just a constant number. So this is not the derivatives that we've been doing. This is going back to calculus 1. This is just the chain rule, where the derivative of y is you bring the exponent in the front, the inside stays the same, and you subtract 1 from the exponent, times the derivative of the inside is just 2x. Or cleaning this up, it's going to be 2 pi x times x squared minus 5 to the pi minus 1 power. However, when we look at example B, notice the difference. Okay, this time the base is constant, not a function of x, and the exponent is a function of x. So in this case, when we take the derivative, it stays the same. times natural log of the base, which is pi, times the derivative of the exponent, which would be 2x. Or in other words, the derivative is 2x times pi to the x squared minus 5 times the natural log of pi. Okay, so just be careful. If it's a function of x, we're doing what we did in Calc 1. If the base is a constant, we're doing this section here. So the derivative of a log with any base is going to be 1 over x times the natural log of the base. Okay? And that would be if the argument is greater than or equal to 0. But it turns out that if you take the derivative of any base with absolute values around the argument, we get the same derivative. Okay? So in general, if you take the derivative of any base, okay, it's 1 over the argument times natural log of the base times the derivative of the argument. So let's find the derivative in the next example, part A. So the derivative, too thick, the derivative of our function is 1 over the argument, right, which would be 2x squared minus 5 times natural log of the base times, and this one involves chain rule, the derivative, I'll write it out, with respect to x, of 2x squared minus 5. Or in other words, the derivative is equal to 4x over 2x squared minus 5 times natural log of 3. Okay, so let's do another example here. S of t is equal to t cubed times log base 2 of t. When I take the derivative here, I need to use the product rule. So my derivative is going to be, I'm going to take the derivative of t cubed, which is 3t squared, and log base 2 of t stays the same, plus t to the third stays the same, times the derivative is going to be 1 over the argument times natural log of 2. Okay, so I don't know if you can see this, but we can reduce by a t, and then we can put all this together as the derivative of s is equal to 3t squared times log base 2 of t plus t squared over natural log of 2. Now, if you're wondering if you can combine this log base 2 and this natural log of 2, you actually can. Of course, I'm not going to require you to do that. But that brings us to this theorem at the very end called the change of base formula. So the change of base formula says that if you have any log with any base, you can break it up. Okay? And what you do is you take whichever base you choose. It could be any base at all. It could even be natural log. And it's the argument over the base. Argument over the base. So what we're going to do is we're going to verify this formula. I'm going to let y equal to log base a of x. Notice in its exponential form, that means it would be a to the y is equal to x. So what we can do in any equation is we can take the log on both sides. So I'm going to take the log base b on both sides of this equation. All right. And then I'm going to try to solve for y. So on the left-hand side, using the properties of logs, I can bring that y out into the front. So it's going to be y times log base b of a, which is equal to log base b of x. And now all I have to do is divide both sides by log base b of a to get log base b of x over log base b of a. And remember what y was in the very beginning. Y was log base a of x. So that just verifies that we can take any base and rewrite our log. Okay? Argument over base. Okay, so that's it for 7.3.